Hi, in this little extra to lecture 2, I want to get some practice in drawing position versus time graphs and also what's called motion diagrams. So let's take this first example. You cycle along at a constant 10 meters per second when you approach a red light. You stop at the light, wait for a few seconds, and then continue your journey. So that's our scenario. And it's asking us to draw a motion diagram and a position versus time graph. We haven't talked about what these ones are, though we have drawn at least one of them already. So this is essentially a representation of the motion in the form of a series of frames, if you like, that are all on top of each other. Let's write this out. Let's see what this means. So showing in a single picture the positions of an object at equally spaced times. Now if that sounds very complicated, think of it this way. Imagine you film with a camera some sort of motion. Then what is a film? What do you have? You have a series of pictures, and they might be, one every 30th of a second or so. Then imagine you take all those pictures and you sort of put them on top of each other, so you can see the object that's moving at all the different positions at equal times. You've done that before with the cyclist, right? And we just drew a dot. So often just draw a dot. Textbook actually goes into quite a bit of detail there, so I suggest you read that. And let's draw one for this particular scenario here. So we want to essentially imagine this is the road, and I'm going to draw the stop sign right here. Sorry, it's a stop light. It doesn't matter. There's my light. Badly drawn. That's it. That's my traffic light. All right, and so I start out here. Like this is my bike. Right. Again, I'm really bad at drawing any bikes or anything really, but that's my bike. Me and my bike. Now, if you imagine I take a movie of this as I watch it, then I put all those pictures on top of each other. I'd see the bike here, then a second later here, second later here, second later here, and so on. But when the bike is slowing down, right, those individual images would be closer together, because what's crucial is that they're at equally spaced times. Now, I'm not going to draw the bike, I'm just going to draw a little dot, right? So right now, it might be looking like this. Right, so these are the individual dots, and you have to choose how far they are apart. Now, this is 10 meters per second, so maybe let's just say it's 1 per second. That's a choice. I could have done 1 per 0.1 seconds, so 1 per, some other sensible choice of time. 1 second is convenient. So after 1 second, it's here. So this is 10 meters. Another second. I don't really care about the numbers right now. I just want to get the shape of it. And then we're slowing down. So that means you're no longer going 10 meters per second, right? 10, 10, 10. Now we're slowing down because there's a red light right here. So maybe now we're going down to 9. Maybe just 7. There. So from one dot to the next, it's always 1 second. And here they're equally spaced. After every second you've gone the same extra distance. You've been going at a constant 10 meters per second. But then we're slowing down, and then really what I have to draw here is a whole bunch of points on top of each other while I'm waiting. Right? If you look again after a second, still in the same spot. Look again after a second, still in the same spot. So I don't know how many. It doesn't tell us exactly how many seconds. A few seconds, maybe 5. The light turns, and now we can go again. So now I start, and I'm probably speeding up, which means that the dots get further apart from one to the next. So I might pick something like this. Then I might keep going at 10 meters per second again. Alright, so this is how I would interpret this. I might just see. Imagine we weren't given the scenario. I was just shown this picture. I could be like, hey, something is moving along at a constant speed. Oh, that must be slowing down because the dots get closer together. So less distance is covered in the same time interval. Even if I don't know what the distances are, or I don't know that it's 1 second from one dot to the next, I can still see that they're slowing down right here, and there are a whole bunch of dots on top of each other, so something must be just sitting there, and then they're getting further apart again, so we're speeding up. It's assuming, of course, I know that the dots are in fact in order. Alright, let's draw a position versus time graph now. This is my motion diagram. So I'm going to pick an origin. Now, you could pick it right here. I'm going to go with the traffic light. It's a nice little reference point. And which way is positive? Well, when we start over here, we end up over there. I guess I'm going to make positive the direction that we're going in. Of course, that is a choice, right? And if you flip it, if I chose a different axis, actually you just flip my graph over. You get practice doing all of that. Okay, let's plot the graph. So to plot the graph, we are going to use a ruler. Keeps it a bit neater. Now, where is my time equals 0? I guess we're going to start the stopwatch right here. Again, not necessary. You could say this is time equals 0. These are negative times. These are positive times. And it's, for example, when you get rid of like a rocket launch and the countdown is negative as you approach the launch, and then becomes positive afterwards. But you know, it's a choice. It's a choice. That's the point here. Right. So we're going to draw a position as time graph. Draw the position, sorry, the time here. I guess it's in seconds. So I'm not really going to worry about numbers. I'm just going to worry about the shape, so we understand what's going on. It's the position in meters. So we're going at a constant speed down here. So where do we start? We start at a negative number. And I don't know what the number is. It doesn't tell us how far away we start. But it's, you know, 10, maybe 50 meters away, maybe 100 meters away, something like that. Let's say we'll start down here. It's a negative position, so this is 0. We'll start down here. I don't know what the value is. Well, given the way I've drawn it, maybe this is minus 50 meters, so it's somewhere below that. And then we're approaching this at a constant speed, so that means straight line, right? So this is for 1, 2, 3, maybe the first 3 or so seconds. Now what happens? We're getting pretty close to the light. We're not quite there yet, but now we're slowing down. So that means we're going to cover less position per time. So we're going the same distance along, the same time along. We're going to go less position up, which means that my graph is sort of becoming more shallow. And then it becomes flat. What's happening here? So maybe if so this is 0 seconds, 1, 2, 3, 4, 5 seconds, maybe after 10 seconds we're here, then I didn't quite draw this very well to scale, I suppose, but when it's perfectly flat, we should be at 10 seconds here. The graph is flat, so that means, I'm going to annotate this in a second, we're not going anywhere, right? Time passes, but we're sitting in the same position, namely right here, and then we start up again, and we speed up, and as you speed up, it means we're getting steeper and steeper and steeper. We pass the light, and then we're going at a constant speed forevermore. So straight line, constant speed. Here, we are slowing down. The graph is becoming more flat, so we are slowing down. Here the graph is flat, position is not changing. So this is where we are waiting. We are at rest. Right, because we're not changing our position. We're sitting at minus 10 meters. So we're sitting there, not getting anywhere no matter how much time passes. Like 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. Okay, now we're going off again. Here we are at this particular point here, we're passing the light. We're passing the origin, right? The position is 0. That is, we're passing the light. And here, well, here we're cycling off into the distance. Again, at a constant speed at the end. That's the scenario. I didn't draw the exact numbers. I made up the numbers as I was going along, except for the initial 10 meters per second. So the point is to understand how the shape of the graph relates to the different stages in the motion, right? Constant speed, constant velocity means straight line at a particular slope that corresponds to the value of the velocity, the magnitude. And it's positive because we're going the same direction as the coordinate axis. Here we're slowing down and the graph is becoming more flat. The slope is getting smaller, right? The slope is the velocity. Then it's flat, so here we're not going anywhere. We're speeding up again, we're passing the light. We're going at a constant speed. And now we're in the positive positions because we're on the right-hand side of the origin, right? The side in where the numbers become positive because we chose our axis to point to the right. Okay, I hope this makes sense. Just an example. Let's do a second example. Second example is this. A ball falls off from a high shelf. It bounces a couple of times and then comes to rest, or a motion diagram and a position versus time graph. Now, if the ball is literally falling down, then what I would do is, this is my shelf, and then this is my shelf. Here's the ball initially, and here's the wall, the floor. Literally what I should be drawing is, let's draw this as the initial position. It's going to be falling, and then it's going to go up, down, up, down, up, down, up, down. But if I do that, I just get so many dots, right? Remember, these are those individual frames from the video that I've made of this, right? My imagined video that makes the motion diagram. It would just go up and down and be a giant mess. So I'm going to pretend it's going a little bit sideways. Then it might look something like this. It's just rolling off the shelf. So I'm just going to track the middle of the ball right here. So maybe a little bit later it's going to be here. And it's probably speeding up as it's falling down, right? Because, well, gravity, we'll talk about that more. Then it's going to go down here. It's going to hit the bottom. It's going to get squished and get pushed back up. And then it's going to do this. Now, realistically, it's not going to get quite as high. So we shouldn't draw it quite as high. Might do something like this. And it's going to hit the ground again. And it's going to go back up again. A little bit less than before. And so on. There's something like this, right? Not drawn like, I didn't take any measurements, I didn't draw it to any scale. But that's the sort of shape you might expect. Right, bounces. They sort of look like a trajectory. That makes sense, right? You're taking a video and you pause every 10th of a second, you might see something like this when you put the pictures on top of each other. Now, this motion as such would be going sideways and up and down. In fact, it's called projectile motion while the thing is in flight. We'll talk about that more too in a little bit. Let's just look at right now let's look at the vertical motion. So I'm going to find my coordinate system to point upwards. I'm going to start up there, point down. I'm going to say the floor is my origin. I'm going to have it point up. But how should we label this? We'll call it X. Often people like to use Y for the vertical direction. I call it Z or Z, right? Why not? Nobody tells me what to do. So let's just draw this. Let's figure out what the graph looks like. I said use a ruler, right? So I better use a ruler. Now, because we know the ball's going to be above the ground, it's never going to be below the ground, we're not going to need any negative positions because that would be below ground. The ball doesn't go there, we know that. And again, we're going to assume that the timing starts here. T equals 0 is at the beginning. It's just convenient to do. Don't have to though, right? You could imagine starting the timer 10 seconds earlier, and then we get 10 seconds of nothing. Actually, let's do it. So we're going to say 10 seconds here before it gets this tiny little push. Just so you can see what it looks like too. So initially the position is going to be some positive value, right? Because it's up here and it's not, 0 is the ground, it's not on the ground, it's up here. So it has to start somewhere up here. What's the value? Well, it's going to be the height of the table, right? Then it's going to start falling, but falling means it's speeding up on its way down, so the line has to become steeper downwards. So it actually looks something like this. Now what happens? Now it's down here, the position is 0, now it's going to go back up. So funnily enough, it's going to reach the top. The graph actually looks sort of like the shape itself, and there's a reason for that, which is that the ball moves at a roughly constant velocity sideways, and that means that the sideways motion kind of acts a little bit like as if it were keeping time. Again, I'm not gonna worry about this. So this is literally a picture of what's happening. I take a picture every 10th of a second. This is a graph of the position, how high up are you up, the vertical position against time. Now it should come to rest eventually, and so I guess I should keep going until this becomes essentially 0. I'm going to stop right here. Maybe I'll just indicate, look, it's going to carry on. So up here, highest point is where we start. It falls down, it gets steeper, that means we're speeding up. The ball is speeding up, it hits the ground, and suddenly it changes direction. It gets squished there for a moment. And it turns around, and it goes back up, it slows down, and we can see it slows down, because the angle of this is becoming more and more shallow. At the top, it's horizontal, which means it's sort of right up here, it's at rest for just a second. And then it gets a negative velocity that gets bigger and bigger, meaning more and more negative. And it starts falling down again, and so on. So, it's just another example. We're going to draw more graphs when we talk about velocity versus time graphs as well, and then it gets a bit more interesting. But right now, you should be in a position, no pun intended, to take some scenario and draw a position versus time graphs, and conversely, if I give you some graph, describe what happens, assuming I tell you what the graph is of what kind of object. Of course, now I made a crucial mistake here, and hopefully you figured it out. I now totally ignored the fact that it was waiting there for 10 seconds. That was supposed to make it more interesting, so I'm going to cheat a bit. I'm going to move my axis back there. Let me see if I can just get rid of this. There is the advantage of using pencil. So, what was the mistake I made? Well, it started right at t equals 0. Really, this should have been 10 seconds. For the first 10 seconds, the ball was at rest. Now, if you were confused, well, good on you. It means you were paying attention. All right. So first 10 seconds, the ball is just sitting at the same position right up there. Only then does it start falling down and following that motion. My mistake. It was a last minute change to have these 10 seconds there. I hope it didn't confuse you. But as I said, if you were confused, that means you actually understood what was going on, which is excellent. Alright, you get lots of practice dealing with those. Thanks for watching once again, and I'll see you in the next lecture.